Hello, physical science class. This is part 2 of your 19A notes, and I wanted to continue looking at the oxidation rules. Oxidation number rule number 4, also known as the zero-sum rule. The sum means you're adding things up, right? If you were to add up all of the oxidation numbers in a compound, that total must equal 0. Charges cannot, or the compound, in other words, cannot be electrically charged. Let me show you what I mean, okay? Sodium is in group 1A, right? That means it has one valence electron. That means it's going to tend, right? If we look back to our rules that we talked about, it's going to tend to give up one valence electron. That would make it, when it gives away a negative charge, would make it be a +1. It's going to tend to look for other elements that want that extra electron, right? When we think about chlorine, for example, it's in group 7A. That means it lacks one valence electron in order to be able to have its perfect 8. So if we think about sodium giving one electron to chlorine, that's going to make chlorine be a -1 in its charge, right? -1 is going to be attracted to a +1, right? So we're going to see that as being table salt's way of combining. Many elements have more than one oxidation number. Just depends on what it can do with its valence electrons. Okay, so when we look at this chart, it's down here in your book, or in your notes, but in the book it's found on page 440, and it's a little bit easier to see because of the colors here. So let me look at an example here. For example, nitrogen, right? Look at all of the possible oxidation numbers that nitrogen can have. That means, and same thing with carbon, or, you know, all of these different other ones where you see multiple oxidation number choices. It just depends on what that element is bonding with. It's flexible, right? So it just depends on what it's bonding with as to what oxidation number it will have. That chart on 440 will be an excellent tool for you to look at and refer to if you have a question. Okay, writing chemical formulas. You need to know the elements and their oxidation numbers in order to be able to write the elements in the proper formula. Okay, you got to write what's happening in real life. You can't just make up something, right? Step 1, you're going to write the symbol of the two elements next to each other. You're going to write the less electronegative element first. Remember, we talked about electronegativity in the last chapter. When we talk about an element that's electronegative, we're looking at the ability to take and hold electrons, right? We could think about it kind of like taking the elements away from another element that's giving up its valence electrons, okay? So when we write that, less electronegative are going to tend to be those elements that are metals, those elements on the left side of the periodic table. And in step 2, we're going to use table 19.1, right? That's this table that I was just talking about here, right? 19.1, to help us to make sure that we're writing the oxidation numbers properly for the two elements. let's think of an example. So potassium chloride is also a particular type of salt, right? We want to write the element with a less electronegativity. Potassium is less electronegative. Chlorine, because it wants its extra electron spot filled, is going to be more electronegative. So we want to write this one on the left side and this one on the right side. We want to use our table 19 to write the correct number of oxidation number, right? So we write potassium as a +1 and chlorine over here as a -1. So we know that those are going to match up, right? Step 3, the quantities of the two elements must be adjusted so that the sum of the oxidation number equals 0. In this case, it was really easy because we have a +1 and a -1. You have one cookie, you eat one cookie, you have none left, right? So the sum of those oxidation numbers is going to equal 0. Then we know potassium chloride is the proper way to write this chemical formula. Where we're going to see this as being a little bit different, let's choose another example. If we said magnesium chloride, and also an example of a common type of salt, magnesium is a +2, and chlorine is a -1, right? These do not equal 0, right? If you have 2 cookies and you eat one, you still have one left, right? +1 is not 0. So we must adjust by adding little subscripts here. So if we were to put a little 2 down here, that 2 is going to essentially be multiplied by this -1, right? So 2 times -1 is a -2, and a +2 plus 2 minus 2 now is 0. So instead of being Mg1 Cl1, our proper way to write this would be MgCl2, right? One other type of scenario would be polyatomic ions. Poly means many. When you have 2 or more covalently bonded atoms bonding together, acting as a single particle, that's going to be a little bit different scenario than what we've talked about here. These are just showing 1, 2, right? When we talk about polyatomic ions, we're talking about things like NH3 or something like that, right? Where you've got more. Okay, the top of the next page has a list of polyatomic ions in chart form, and this chart is found in your book on page 441, and that is also extremely handy, especially when we're learning about how to properly write things. What this is telling us is that there are special names for those polyatomic ions, and those names are going to help us when we name things. Okay, we'll come back to this at a later date. Oxidation rule number 5 would be the sum of the oxidation numbers of all atoms in a polyatomic ion equals the charge, right? Hydroxide ion, OH negative, is going to, that's okay. It does not have to equal 0. It's going to equal the charge because it's a polyatomic ion, right? It's got a charge, and it's allowed to have a charge. It doesn't have to be neutral. So that would be rule number 5. Naming a compound. We're going to pick up with this a little bit more as we are learning about naming things, but I just want to give a couple of details here. Binary compounds have a first and last name, right? Bi means two, so we're going to have a first and last name essentially, right? If you have a metal, you're going to put that metal's name first. Like we said, magnesium, right? Magnesium is a metal. It's going to go first in the name. A non-metal is going to have the second part, right? The last name, if you will. So what we're going to do is take let's see, carbon dioxide, for example. If we said carbon dioxide, it's going to be carbon, di means two, and oxygen means that it's the second half, right? The non-metal. And what we've done is we take oxygen and we chop off the ending and slap on IDE, right? Oxide. So that tells us carbon dioxide, di is related to prefixes. There are prefixes that are going to help us to know how to read how many of each one there are. And there's an important chart on page 443 that shows these prefixes. Right? So di means two, tri means three, tetra means four, penta means five, right? Those are going to be helpful because we would know that this is carbon dioxide. We could say CO2, right? Compounds with polyatomic ions. The first name is going to be that of the cation. The positive oxidation number goes first. The second name is going to be that which ends in IDE and is going to be anion, which is negative. Okay? So that's going to be helpful as well to give us those rules. Thanks. This is the end of our note.